two projects. In this video, we are going to explain about the project title, Predicting Coronary Heart Disease Using an Improved Light GBM Model, Performance Analysis and Comparison. Introduction. CHD, a prevalent cardiovascular disorder, is primarily caused by the accumulation of atherosclerotic plaques in the coronary arteries. These plaques reduce blood flow to the heart muscle, leading to severe health implications. Traditional methods for CHD prediction often lack accuracy and efficiency. This is attributed to their reliance on simplistic models and limited feature analysis, which may not effectively capture the complexity of the disease. Early detection of CHD is emphasized due to its critical role in improving cure probabilities and reducing overall treatment cost. Timely identification allows for proactive intervention and better disease management. Machine learning algorithms and data mining technologies have become integral tools in the medical field for disease prediction and analysis, including CHD. These technologies allow for the development of more sophisticated models that can leverage a wider range of features and data, potentially leading to more accurate predictions. Hyperparameter optimization is highlighted as a critical factor in improving the accuracy of classification algorithms like light GBM. Fine-tuning hyperparameters ensures that the model is optimized to perform efficiently, resulting in a more accurate prediction of CHD. Objective. The primary goal is to create the HY-opt GBM prediction model, leveraging the light GBM classifier. This model will be designed to accurately predict coronary heart disease CHD by optimizing the hyperparameters and loss function associated with the light GBM classifier. The project aims to improve the early detection of coronary heart disease CHD within the general population. This enhancement is crucial as it facilitates timely treatment by healthcare professionals, potentially leading to better outcomes for individuals while also potentially reducing the costs associated with medical treatment for CHD. The project involves evaluating the performance of the prediction model using CHD data from the Framingham Heart Institute. This evaluation includes comparing the HY-opt GBM model with other existing models, assessing its efficacy and superiority in predicting CHD. A significant aspect of the project is the emphasis on optimizing the light GBM model's loss function. The focal loss FL method is specifically utilized for this purpose, aiming to address imbalanced proportions of positive and negative samples within the dataset. This optimization contributes to more accurate predictions in the context of CHD. Requirements. The requirements of the project are hardware requirements, in which we have operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements, in which we have Anaconda 3 and Visual Studio Community version. Flow of work. To implement this project, we have designed the following steps. The first step is importing the packages. Necessary libraries and modules are imported, such as Pandas for data manipulation, Seaborn and Matplotlib for visualization, label encoder for label encoding, and likely light GBM for model implementation. Exploring the dataset. Framingham heart disease data. The dataset related to Framingham heart disease is loaded and explored to understand its structure, features, and content. Data processing. Pandas data frame. The dataset is organized into a Pandas data frame, a structured format that allows for efficient data manipulation and analysis. Cleaning the dataset. Data cleaning operations are performed to handle missing values, remove duplicates, or address any anomalies in the dataset that might affect model performance. Visualization using Seaborn and Matplotlib. Data visualization techniques using Seaborn and Matplotlib are applied to gain insights into the dataset, such as distribution of features, correlation between variables, and any potential patterns. Label encoding using label encoder. Categorical variables are encoded into numerical values using label encoder, making the data compatible for machine learning algorithms that require numerical inputs. Smart sampling the dataset. Synthetic minority oversampling technique is applied to balance the class distribution in the dataset, particularly important if the data is imbalanced to ensure unbiased learning by the model. Splitting the data to train and test. The dataset is divided into training and testing sets, with a portion allocated for training the model training set and another for evaluating the model's performance testing set. Building the model. This step involves setting up the structure for various models that will be used in the project for predicting coronary heart disease CHD. ADA Boost, Adaptive Boosting. ADA Boost is an ensemble learning method that combines the predictions of several weak learners, typically decision tree, to create a strong predictive model. It focuses on improving the classification of difficult instances by giving more weight to misclassified samples. Decision tree. Decision trees are a fundamental type of model in machine learning. They recursively split the dataset based on features to make predictions. Each split is based on maximizing information gain or Gini impurity, aiming to create distinct groups with homogeneous target values. Bagging. Bootstrap aggregating. Bagging involves training multiple instances of a model on different bootstrap samples of the dataset, sampling with replacement. The final prediction is usually an average of voting of the predictions from these models, reducing overfitting and improving stability. Gradient boosting. Gradient boosting is an ensemble learning method that builds models sequentially. Each model corrects the errors made by the previous one. It minimizes a loss function, often using decision trees as weak learners, resulting in a strong predictive model. XGBoost, Extreme Gradient Boosting. XGBoost is an efficient and scalable implementation of gradient boosting. It provides regularization techniques, parallelization, and handles missing data, making it popular for its performance and effectiveness in various predictive modeling tasks. CatBoost. CatBoost is a gradient boosting library that excels in handling categorical data. It automatically deals with categorical features and does not require extensive pre-processing, making it efficient and convenient for a wide range of datasets. Light GBM with focal loss. Light GBM is a gradient boosting framework that's efficient and scalable. It uses a histogram-based learning approach and can handle large datasets in high-dimensional feature spaces. It's known for its speed and performance. Focal loss is a modification to the standard loss function in binary classification problems. It addresses class imbalance by giving more weight to misclassified samples. Integrating this into light GBM can improve its performance, especially when dealing with imbalanced data. Light GBM without focal loss. This refers to using light GBM without integrating the focal loss function. It's the standard usage of light GBM for binary classification without the adjustments made by focal loss. Training the model. After building the models, this step involves feeding the training data into these models. The models learn patterns and features from the data to make accurate predictions during CHD. Flask framework with SQLite for sign up and sign in. Utilizing Flask, a web framework in Python, combined with SQLite, a lightweight database, allows the creation of a user authentication system. Users can sign up and sign in to access the system securely. User gives input as feature values. The project begins with the user providing input in the form of feature values related to coronary heart disease CHD prediction. These features could include various health-related parameters such as age, blood pressure, cholesterol levels, etc. The given input is pre-processed for prediction. The input provided by the user is pre-processed to ensure it's in the suitable format and structure expected by the trained model. This step involves any necessary transformations, data formatting, or feature scaling to prepare the input for prediction. Trained model is used for prediction. The pre-processed input is then fed into the trained model. Example, light GBM that was built and optimized in earlier steps of the project. The trained model processes the input based on its learned patterns and provides a prediction regarding the likelihood of the user having coronary heart disease. Final outcome is displayed through front end. The prediction outcome generated by the trained model is then displayed to the user through the front end of the application. This could be a simple interface where the user can view the prediction result, which might indicate the probability or prediction of coronary heart disease. Accuracy comparison graph. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm names. And from this graph, we can say that the ensemble models are performing well. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances to the total number of instances. Precision comparison graph. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. And from this graph, we can say that the ensemble models are performing well. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives to the total number of positive predictions. True positives plus false positives. Recall comparison graph. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. And from this graph, we can say that the ensemble models are performing well. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances. True positives plus false positive. FN comparison graph. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. And from this graph, we can say that the ensemble models are performing well. The FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is the model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynd file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost, and port, which is this. Now copy this local link. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. This is the homepage of the project displayed in the browser. This is the front end built using Flask framework. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate prediction. Now click on sign up button to register. If we are a new user, we need to register first, but I have already registered. So click on I'm already a member link. Here we need to enter the username and the password which we have created and then click on login. We have logged in. So here we need to enter all these parameters to predict whether the person is having coronary heart disease or not. So I'm entering the parameters. The first one is sex, whether the person is male or female. So here the person is male, that is 1. And the age of the person is 39 years. And current smoker, whether the person is smoking currently or not. So here the person is not smoking currently, that's why it's 0. And cigarettes per day is also 0 because the person doesn't smoke. And prevalent hypertension is also 0, that is the person is not having the hypertension. Total cholesterol is also 0, that is the person is not having the cholesterol. And SYS BP, that is systolic blood pressure, is also 0, that is the person is not having the systolic blood pressure. And systolic blood pressure is also 0, that is the person is not having systolic blood pressure. And BMI, body mass index, is 26.9. Heart rate is 80. Glucose is 88. After entering all these parameters, click on predict. So here we got the outcome, that is there is no risk of coronary heart disease CHD after 10 years. So this person is not having the coronary heart disease. Now we will enter another set of parameters and predict whether that person is having the coronary heart disease or not. So here I'm entering the sex as female, which is 0, and the age of the person is 61 years. And current smoker is 1, that is the person is smoking, and cigarettes per day is 30. And prevalent hypertension is 0, that is the person is not having the hypertension. And total cholesterol is also 0, that is the person is not having the cholesterol. And systolic blood pressure is 1, that is the person is having the systolic blood pressure. And diastolic blood pressure is 0, that is the person is not having diastolic blood pressure. And body mass index of the person is 28.58. And heart rate is 65. And the glucose is 103. After entering all these parameters, click on predict. So here we got the outcome. There is no risk of coronary heart disease CHD after 10 years. Even this person is not having the risk of coronary heart disease. We will enter another set of parameters. So I'm entering the parameters now. So here I have entered another set of parameters. Sex is 0, that is it is a female, and the age of the person is 61 years. Current smoker, that is 1, it means the person is smoking correctly. And cigarettes per day is 30, and prevalent hypertension is 0, that is the person is not having hypertension. And total cholesterol is also 0, that means the person is not having the cholesterol. And systolic blood pressure is 150. And the diastolic blood pressure is 95, body mass index is 28.58, heart rate is 65, and the glucose levels is 103. After entering all these parameters, click on predict. So here we got the outcome, that is there is a risk of coronary heart disease CHD after 10 years. This means the person is having the risk of coronary heart disease. In this way, by entering the parameters, we can predict whether the person is having the risk of coronary heart disease or not. And the conclusion of the project is, the project introduces HY-opt GBM, a prediction model leveraging an optimized light GBM classifier and an improved loss function. This model showcases high accuracy in predicting coronary heart disease, suggesting its potential effectiveness in healthcare applications. The model's performance is rigorously evaluated using essential metrics: precision, recall, F-score, and accuracy. These metrics provide a comprehensive assessment of the model's ability to predict CHD accurately and reliably. The project highlights the implementation of optimization efforts, including refined loss functions and advanced classifier techniques. These enhancements are integrated to create the HY-opt GBM prediction model, which is expected to offer improved accuracy and efficiency in CHD prediction. Early accurate prediction of CHD using the HY-opt GBM model has the potential to lead to significant cost savings in the medical treatment of CHD patients. By enabling early intervention and timely allocation of resources, it optimizes healthcare spending and reduces financial burden on both individuals and healthcare systems. The project emphasizes that timely intervention facilitated by accurate CHD prediction can optimize healthcare spending and resource utilization. It ensures that resources are allocated efficiently, allowing for better healthcare delivery and cost effective management of CHD cases.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.